Calculus 1 project for Mr. Kellum's class. This video will be sponsored by Kirby's Land Services. Call either of these two numbers here. They do all these things, so yeah, pretty good. So let's get started. All right, guys, so I got a stopwatch here, a ball here, Chuck E. Cheese, and I got tape. Come a little closer. I got tape marking out 4 foot apart. I have 1, 2, 3, 4, 5, 6 pieces of tape. I'm starting here. They're all 4 foot apart. Now let's get this ball rolling. 3, 2, 1. All right, ball's gone. But I got 5 seconds here. It's raining, but I forgot to mention a couple things. Lightning has been detected, and I'm holding a selfie stick right now, so it's probably not the best idea. There's the thunder. I forgot to mention a couple things. The tape was there. It's not there, but it was there so that we could calculate the instantaneous velocity. I went back in the video. It was just under 5 seconds, so it wasn't actually 5 seconds, but I do have those values written down. We're gonna get those plugged into Excel, and that's gonna give us our graph and our equation for our line, and we're gonna use that to find the instantaneous velocity at each point. And after we get that, we're gonna compare them just to see how much faster it gets as it goes down the hill. But let's get back inside, because I'm not trying to get struck by lightning today, so let's get to it.
All right, so this is Excel. This is where I'm gonna plug in my time. I'll plug in my distances here as well, and that's going to give me a graph so I can look at the points and how the graph changes over a period of time. This will help me find my instantaneous velocity by giving me the equation to the graph. I will then take the derivative of the equation and then plug in my times to get an instantaneous velocity for that point. These times are actually the times that I come up with by going back and watching the video. The distances, I'm going to use increments, as you can see here. I won't be putting in the exact footage, just using increments. That makes the graph a little easier to see for me. And yeah, so. All right, as you can see, our graph has been generated, and from here we're going to go ahead and add our trend line and find the equation for our graph. All right, so this is our lines equation, but I'll explain more about how this is going to be used to help us find our instantaneous velocity in the next clip. All right, so here's our equation for our line, and here is a little side note. So S of t is our position, and the S prime of t is our velocity at a certain time or point, which is also our instantaneous velocity. So this can be called our position function, so S of t. And the S prime of t will be 0.5932x minus 0.0066. And this is a constant, so it goes to nothing. So what we will do is we will plug our times in for x, and that will give us our instantaneous velocity. So let's go ahead and get into that. So I forgot to mention that the values that we just got were in feet per second, and that I will also be taking the average velocity of the ball going down the hill. To do that, I'm just going to be plugging in my first point and my last point into slope formula. That's going to give me my average. All right, so that's how you find the instantaneous velocity of a ball rolling down a hill. I don't think that it was that difficult, but I do think that you need to know some calculus before you do the experiment. I thought it was pretty fun to see all the things on paper and on the graph, but as far as concluding goes, Mr. Kellum said it first, so
Hopefully you get a lot from this.